Our next section in Chapter 8, we are going to cover implicit differentiation. I'm going to do a quick review first. The derivative of x squared, we use the power rule, says bring down the exponent and subtract 1 from the exponent. Another review, derivative of sine squared x. This is chain rule, where the outside function is equal to x squared. The inside function is equal to sine of x. Three-step chain rule says take the derivative of the outside function, except don't write x. Where x goes, you write the derivative, you write the inside function, times the derivative of the inside function. Derivative of sine is cosine x. So, just a quick review. Next I want to do is I want to find dy dx of x plus y squared 25. So far, when we've been asked to find the derivative, we've been asked to find the derivative of functions. You should remember that this is the equation for a circle centered at the origin with a radius of 5. That is not a function. It does not pass the vertical line test. So one way that you could find dy dx is actually solve for y, but then you're going to end up with two equations that you will have for derivatives. So for the first example, let's solve this for y. You get y squared equals 25 minus x squared. To solve for y, you get y equals plus or minus the square root of 25 minus x squared. Well, in order to find dy dx, it depends upon if you're talking about the upper half of the semicircle or the lower half of the semicircle, which one of these you want to take the derivative of. So I'm going to just take the derivative of the upper semicircle. Well, to find dy dx, take the derivative of the left-hand side. Dy dx is equal to, this is a chain rule problem. The outside function is the square root of x, or another way to think about it is x to the 1/2. The inside function is 25 minus x squared. So to find the derivative, we take the derivative of the outside function, which says bring down the exponent, subtract 1 from the exponent, but don't write x. So I get 1/2 something to the negative 1/2 power. Where x goes, you put the inside function, 25 minus x squared, times the derivative of the inside function. The derivative of 25 minus x squared is negative 2x. Simplifying, negative 2x divided by 2 is negative x over 25 minus x squared underneath the square root symbol. Notice this equation, I could solve for y, and then once I knew which portion of the curve, whether it was the upper semicircle or lower semicircle, I could actually take the derivative. However, we're going to come across equations, for example, x to the 6th plus x to the 4th y squared plus y cubed equals a number. And we're going to want to be able to analyze to find what is the slope of this curve at particular values. For example, I want to know what is the slope of the curve at the point x11 for this function. So in order to do that, we need to come up with another way to differentiate this function. So, in order to do this, let's do another something squared. Here we go. And let's just look at this. I want to find d over dx of y squared. What's the derivative of y squared? Well, that's the derivative of something squared. Well, let's see, what did we do here? The derivative of something squared was 2 times that something times the derivative of that something. Derivative of x is 1. The derivative of something squared is 2 times the something times the derivative of the something. So the derivative of something squared is 2 times the something times the derivative of the something. The derivative of y with respect to x is dy dx. So using intuition, this is what we should get for the answer. Well, there's a way to formally come up with what the derivative of y squared is. We use the previous section of the chapter where we talk about the chain rule, where we have two functions. So I want to find dy of dx of y squared. Well, this is chain rule, where I have an inside function of y, I have an outside function of x squared. Well, the chain rule says to take the derivative of the outside function, except don't write x. Where x goes, you put the inside function, times the derivative of the inside function. The derivative of y with respect to x is dy dx. Notice I got the exact same answer. So let's go back to the one that I could solve before. The derivative of x squared plus y squared equals 25. And let's do it the second way. And let's see if we get the same answer. Well, let's take the derivative of x squared. That's 2x. The derivative of y squared is 2y dy dx. The derivative of 25 is 0. I want to solve for dy dx. So that says to subtract 2x from both sides. So I get 2y dy dx equals negative 2x. Divide both sides by 2y, and I get dy dx equals negative 2x over 2y, which is negative x over y. Now, if I wanted to evaluate this derivative at a point, for example, at 1/2 square root of 3 over 2, which is this was 1. So it would be 1/2 times 5 square root of 3 over 2. I would be able to analyze just by putting these coordinates in, but that looks different than my other answer. Well, remember that when I solved for y, I got y equals plus or minus the square root of 25 minus x squared. And if I'm interested about that upper half of the semicircle, where I just take the positive one, I could have rewritten this negative x over what's y equal to? Well, it's 25 minus x squared. So this is identical to what I got before. Okay. However, I cannot solve this equation for y. So I have to use this second method called implicit differentiation to find out what dy dx is. So let's figure out what dy dx is and then evaluate. I want to know what dy dx is evaluated at the point 1, 1. I wanted to know the slope of the tangent line at the coordinates 1, 1. So, chain rule. Power rule first. I have 6x to the 5th power. This is product rule. It's the first function times the derivative of the second, which is 2y dy dx, plus the second function times the derivative of the first, which would be 4x cubed, plus derivative of y cubed would be 3y squared dy dx, and the derivative of 3 is 0. So what I need to do now is I need to solve the equation for dy dx. In order to solve for dy dx, I need to move everything that does not have a dy dx in it to the right-hand side of the equation. So on the left-hand side, I'm going to end up with 2x to the 4th y dy dx. 2x to the 4th y dy dx. I'm going to end up with the 3y squared dy dx. I am going to move this term that doesn't have a dy dx and this term that doesn't have a dy dx to the right-hand side. So So I get negative 6x to the fifth minus 4x cubed y squared. Notice that each term on the left-hand side has a dy dx. I can factor the dy dx out. And I am left with 2x to the fourth y plus 3y squared. And I get negative 6x to the fifth minus 4x cubed y squared. Last step is to divide both sides by what's inside the brackets here. So I have my derivative of my function, dy dx, is equal to negative 6x to the fifth minus 4x cubed y squared over 2x to the fourth y plus 3y squared. So I have solved for dy dx, but I want to evaluate it when x is 1 and y is 1 to find the slope of the tangent line to the curve that's represented by that equation. Well, let's put a 1 in for x and a 1 in for y. 1 to any power is 1, so I get negative 6 minus 4, which is negative 10 in the numerator. I get 2 plus 3, which is 5 in the denominator, and I get negative 10 over 5. So dy dx evaluated at the point 1, 1 is equal to negative 2. So the slope of the tangent line to the curve that's graphed by this equation is negative 2.